8.10, putting it together. In this lesson, we will use everything we've learned about derivatives to analyze functions and their graphs. A very quick review of what we've learned. The first derivative tells us if our function is increasing or decreasing. The second derivative tells us if it's concave up or concave down. We have critical points when the derivative is 0 or does not exist. When the derivative is 0, we can use the first derivative or the second derivative test to figure out if it's a maximum or a minimum. For example, if the second derivative is negative, we have a maximum. When the second derivative is positive, we have a minimum. The mean value theorem tells us that if the average rate of change in an interval is some number, say 3, there is some point in that interval such that the slope is exactly 3. Finally, review from before, derivatives do not exist if we make sharp turns. So at the point where we make sharp turns, the derivative does not exist. Okay, let's look at some examples. Example 1. A of x is equal to 1/3 x cubed minus 4x squared plus 12x minus 2. Part A. Find all the critical points of A. Identify if A has a maxima or minima at each of these points. Justify your answer. So to find critical points, we have to take the derivative. So a prime of x equals the derivative of 1/3 x cubed is x squared. The derivative of minus 4x squared is negative 8x. The derivative of plus 12x is plus 12. And the derivative of negative 2 is 0. So the derivative of x squared, the derivative of a is x squared minus 8x plus 12. At critical points, well, this is a quadratic, so it's defined everywhere. So we want to find where the derivative is 0. We factor this quadratic, we get x minus 2 times x minus 6, because negative 2 times negative 6 is plus 12. Negative 2 plus negative 6 is negative 8, equals 0. So we get x equals 2, x equals 6. So we have critical points at x equals 2 or x equals 6. To figure out if they're maxima or minima, let's use the second derivative test. The second derivative is equal to 2x minus 8. At x equals 2, the second derivative equals negative 4, which is negative. When the second derivative is negative, we have a maxima. And at x equals 6, second derivative is plus 4, which is positive, which tells us that that is a minima by the second derivative test. B. Identify the intervals for which f of x is increasing. Okay, here it might help if we quickly sketch our graph. So here's our axes. We know that the graph has a maxima at x equals 2 and a minima at x equals 6. So that means that our graph looks like this. It's also x cubed, it's a cubic, so our graph looks like this. So from this sketch graph, it looks like a of x should be increasing. It's increasing in the intervals, well, from negative infinity to 2, because that's where it gets to a maxima, and from 6 to positive infinity. Okay. To justify our answer, we see that the graph, we know that this first derivative is x squared minus 8x plus 12. And we can check. Let's use our testing points. Let's use a of 0. Well, a of 0 is plus 12. So it's positive. A of 4 is 16 minus 32 plus 12, which is negative. Is negative. And a of 8 is positive. So that tells us that the first derivative is positive when x is less than 2 or x is greater than 6. So that's why a of x is increasing in those intervals, because the first derivative is positive. Part C. Explain why there must be a point C in the interval 4, 6 such that the second derivative is 0. Well, we know that our derivative a prime of x is 0 at x equals 4 and x equals 6. So the average rate of change of the first derivative of x must be 0 in the interval from x equals 4 to x equals 6. If it's 0 at 4 and 0 at 6, the average rate of change must also be 0. So by the mean value theorem, there must be a point C in the interval for 6 such that the slope must be equal. In this case, we're talking about the slope of the first derivative must be equal to the average rate of change, which is 0. Okay, and that point is C. Example 2. In the open interval 0, 2, a particle is moving along the y-axis. The particle's velocity is given by v of t is equal to 3 sine t cosine t. The acceleration is given by a of t is equal to 3 times cosine squared t minus sine squared t. We know that the acceleration is really just the derivative of the velocity. A. Is the speed of the particle increasing or decreasing at t equals 1.8? Explain your answer. The speed is so if you look at the velocity, v at 1.8 is equal to 3 sine 1.8 cosine 1.8. When we plug that into Google, we get negative 0.66, which is negative. That's the key. So velocity is negative. The acceleration at 1.8 is equal to 3 cosine 1.8 squared minus sine 1.8 squared. Okay. Let's plug that in to Google. We can use a calculator for this one. 3 times cosine 1.8 squared minus sine 1.8 squared. I'll also get a negative number. So it's equal to around negative 2.69. They're both negative. Okay, what does that mean? Well, when v is 1.8, that means when the v is negative, that means that our graph is going down, like that. And when the acceleration is negative, that means concave down. So it looks like this. So that means our graph of our particle must be moving. It must be concave down and negative. When it's concave down and negative, it's becoming more and more negative very quickly. That means that the particle is moving downwards and concave down. So it is speeding up because it's going down more and more quickly. It's going in a down direction more and more quickly. So it's actually speeding up. So the speed is increasing. B. in the interval 0, 2, the particle changes its direction exactly 1. At what time does the particle change direction? So when it changes direction, we know that the graph must be going up and then down, or down and then up. That means the first derivative is 0. The velocity is 0. So the velocity is 3 sine t cosine t, which is equal to 0. So we want to solve the equation 3 sine t cosine t equals to 0. Well, that means that either sine t is equal to 0 or cosine t is equal to 0. We know that sine t is equal to 0 when t equals 0, and cosine t is equal to 0 when t is equal to pi. But we're looking for the interval 0, 2. We're looking for this interval, the closed interval 0, 2, including 0 and 2. And pi is outside of that interval. So we know that we're looking for t equals 0. Okay. C. What is the position of the particle when it changes direction? Okay. This one we will actually skip, even though this is actually an MCAS question. We know how to go from velocity to acceleration. We don't know yet how to go from velocity. Don't know yet how to go from velocity to position. We need the opposite of derivative, which is integration, which we will learn in the next unit. We will learn in Unit 9. Is the position at a maximum or minimum when it changes direction? Okay, well, we can use the second derivative test. Maximum means the second derivative is negative. Positive means the second when the second derivative is positive, we have a minimum. So it changes direction at t equals 0. A of 0 is equal to 3 times cosine 0 square minus sine 0 square, which is equal to 3 times 1 minus 0, which is equal to 3. So it's positive. Because it's positive, we have a minimum point by the second derivative test. Okay. Example 3. The height of a roller coaster over time is given by the function f of t is equal to e to the sine t power minus 0.368 for t in the interval 0 in the open interval 0, 3. Find the time when the height of the roller coaster is at its maximum. Justify your answer. So again, maximum means critical point. Maximum means first derivative is 0 and second derivative is negative. That's what we're looking for. So let's find the first and the second derivatives. So the first derivative must be e to the sine t power times cosine t because of chain rule. Okay. When that's equal to 0, well, e to the any power can't be 0. It's always positive. Times cosine t. That means that we're looking for cosine t equals 0, which means t equals 90 degrees, which is equal to pi over 2 in terms of radians. Okay. Is it actually at its maximum? Let's check. The second derivative at pi over 2. Let's take the derivative. Okay. We need to first use the product rule. The derivative of the first term, again, is e to the sine t power times cosine t, times the second term, cosine t, plus the first term, e to the sine t, times the derivative of the second term, negative sine t. Okay. That's equal to, we know pi over 2 is really just 90 degrees, so it's really the second derivative of 90 degrees, which is equal to e to the sine of 90 degrees. Sine of 90 degrees is 1, times cosine 90 degrees, which is 0, times cosine 90 degrees, which is 0, plus e to the sine 90 degrees, which is 1, times negative sine to the 90 degree, which is negative 1. So it's equal to negative e. If the second derivative is negative, we know it's maximum. So we know f is at a maximum at t equals pi over 2 by the second derivative test again. Example 4. In example 4, we're given the graph of the first derivative f prime x. The graph goes up in a straight line from -6 to -3 for x, and then it goes up in a curved line from -3 to -1, and then it makes a sharp turn, and it goes down in a straight line to 5, and then it makes another sharp turn, and it goes up in a straight line to 7. Okay, so A, on what intervals is f of x decreasing? Justify your answer. Well, f of x is decreasing when our first derivative is negative. Our first derivative is less than 0 when in the intervals -6, -3, an open interval -6, -3, and the interval open interval -1 to 5. That's when the first derivative is decreasing. Sorry, that is incorrect. We're looking, because the function is decreasing, we want our first derivative to be negative. Our first derivative is negative in the intervals -6, -3, and the open interval 3 to 7. That's when our graph is negative. So right here, and also right here. When it's negative, our function is decreasing. B, on what intervals is f of x concave up? Justify your answer. Well, f of x is concave up when the second derivative is positive, and our second derivative is positive when our first derivative is increasing. Our first derivative is increasing in the intervals -6 to -1, and also 5 to 7. Because the first derivative is increasing, f of x is concave up. C, does the second derivative of -1 exist? Well, the first derivative at -1 makes a sharp turn. So f prime of x makes a sharp turn at x equals -1. So the derivative of f prime of x does not exist. So the second derivative at x equals -1 does not exist. We can't calculate the slope of our line right here. It's making a sharp turn. Last part. Does f prime prime 6 exist? Does the second derivative exist at x equals 6? If yes, what is it? Well, at x equals 6, our derivative is making it in a straight line. That's okay. So our first derivative has a defined slope. What's that defined slope? Well, the line is going up 2 and going to the right 2. So the slope must be 2 over 2, which is 1. So the first derivative has a defined slope of 1 at x equals 6. So our first derivative at x equals 6 is just 1, because the second derivative is just the is just the slope of the first derivative. Okay, that's it.